What is a cost function? If you have ever seen a neural network learn, you have seen the cost function at work even if you did not know it. Every single weight update, every backpropagation step, every epoch of training, all of it is driven by one number. That number is the cost function. Here is the simplest way to say it. The cost function measures how wrong the model is right now. It takes the model's predictions and compares them to the truth, and collapses that comparison into a single scalar. One number. Lower is always better. 0 means perfect. This video is part of the Maths Behind AI series from Neural Monk. We are going to build up the complete picture, from the intuition of what a cost function is, through MSE, cross-entropy, MA, Huber loss, all the way to how you use these in a real PyTorch training loop. Let us begin. Before we get into any specific formulas, let us build the intuition from scratch. Imagine you have trained a model to predict house prices. You feed it a house with 3 bedrooms and 2 bathrooms, and it predicts the price is $300,000. The actual sale price was $350,000. The model was wrong by $50,000. Now do that for 10,000 houses. Each one has an error, a gap between what the model predicted and what the truth was. The cost function is a way of collapsing all of those individual errors into a single number that tells us, overall, how wrong is this model? Why do we need a single number? Because gradient descent needs one. The optimizer needs to be able to say, did this parameter update make things better or worse? A single scalar gives a clear answer. A lower number means better. The gradient of that number tells the optimizer which direction to push each weight. So the cost function has 4 essential properties. It must be non-negative, loss cannot be below 0. It must be differentiable, we need to be able to compute its gradient. It should equal 0 for a perfect model. And it must be a scalar, not a vector, so gradient descent has a single objective to minimize. The most fundamental and widely used cost function for regression problems is mean squared error, or MSE. Let us build it step by step from first principles. Suppose the model predicts 3.4 but the true value is 3.0. The error is 0.4. We square it to get 0.16. Why square it? 2 reasons. First, squaring makes the error positive regardless of direction, whether the model overpredicts or underpredicts, we get a positive penalty. Second, squaring amplifies large errors much more than small ones. An error of 2 is penalized 4 times more than an error of 1. The optimizer is strongly pushed to fix the big mistakes first. We do this for every training sample, sum all the squared errors, then divide by n to get the mean. That is MSE. The gradient of MSE with respect to a weight W is 2 over n, times the sum of the prediction error multiplied by the input feature. This gradient flows directly into gradient descent, nudging the weights in the direction that reduces the average squared error. MSE is convex, it has exactly one global minimum. This means gradient descent is guaranteed to find the optimal solution for linear regression. It is differentiable everywhere. And it is interpretable, MSE equals 0 only when predictions are perfect. For classification problems, predicting categories rather than continuous numbers, the standard cost function is cross-entropy loss. Here is why MSE does not work well for classification. If you are predicting probabilities, you need a function that heavily penalizes confident wrong answers. If the model says there is a 99% chance of cat, but the answer is dog, that needs to be penalized catastrophically. MSE would give you a squared error of about 0.98. Cross-entropy gives you the logarithm of the predicted probability for the true class, and log of 0.01 is negative 4.6. That is a massive penalty. Cross-entropy loss for multiclass problems is negative sum of y times log of y hat, where y is the one-hot true label vector and y hat is the softmax predicted probability distribution. For the correct class where y equals 1, the loss is negative log of the predicted probability. All other classes contribute 0 because y is 0 for them. The intuition is clean, the loss pushes the predicted probability for the true class toward 1. The closer to 1, the lower the log, the lower the loss. Wrong class predicted with high confidence, log approaches 0, so the negative is a very large number. For binary classification, two classes like yes or no, we use binary cross-entropy, which is a simplified form, negative y log p minus 1 minus y times log 1 minus p. MSE has a significant weakness: it is sensitive to outliers. Suppose you are predicting house prices. 99 houses have prediction errors under $10,000. One house, which is a bizarre celebrity mansion, has a prediction error of $1 million. The MSE will be dominated by that one outlier. Its squared error is a trillion times larger than the others. The model will spend most of its effort minimizing that one extreme case, at the cost of the 99 normal ones. Mean absolute error, or MAE, solves this. Instead of squaring the error, you take the absolute value. An outlier with an error of 1 million contributes linearly 1 million to the total, not quadratically. The gradient of MAE with respect to the prediction is simply plus 1 or minus 1, the sign of the error. This is robust but has a problem: the gradient is constant regardless of how large the error is. Near the minimum, the gradient does not shrink, which makes convergence unstable. Huber loss is the best of both worlds. It behaves like MSE for small errors within a threshold delta and like MAE for large errors above delta. Below the threshold it is smooth and has gradients proportional to error size. Above the threshold it is robust like MAE. The threshold delta is a hyperparameter, typically set to 1. Huber loss is used extensively in reinforcement learning, where outlier rewards can destabilize training, and in robust regression tasks where your data has noise and anomalies. Let us think visually about what the cost function actually looks like. For a model with a single weight, the cost function is a curve in 2 dimensions. The horizontal axis is the weight value. The vertical axis is the cost. For MSE with a linear model, this curve is a parabola, a smooth bowl shape. There is one valley at the bottom. That valley is the optimal weight. Gradient descent rolls a ball down this bowl toward the minimum. For a model with 2 weights, the cost function becomes a surface in 3 dimensions, like a hilly terrain. You can visualize contour lines on this surface just like a topographic map. The minimum is the lowest valley. Gradient descent follows the steepest downhill path on this surface. For a real neural network with millions of weights, the cost function is a surface in a space with millions of dimensions. You cannot visualize it, but the principle is identical. The gradient vector points uphill in this high-dimensional space. Gradient descent steps in the exact opposite direction. This visual mental model is important because it explains everything about training behavior. Why does learning slow down near the end? Because the loss surface is nearly flat near the minimum, gradients are small. Why do some models get stuck? Because the surface has local valleys or flat plateaus. Why does learning rate matter? Because the step size determines how far down the surface we move each iteration. The gradient of the cost function is the engine that makes learning happen. Let us understand it precisely. For a one-dimensional model with a single weight, the gradient is just the derivative, dj divided by dw. At any point on the loss curve, this derivative gives the slope. If the slope is positive, the cost increases as w increases, so we decrease w. If the slope is negative, the cost decreases as w increases, so we increase w. If the slope is 0, we are at the minimum, no update needed. For MSA, this gradient is 2 over n times the sum of the prediction error multiplied by the input. You can derive this by differentiating the MSE formula with respect to w. The 2 comes from the chain rule applied to the square. The x comes from differentiating the linear prediction y hat equals wx plus b with respect to w. For a real neural network with millions of weights, there is a partial derivative for each weight. How does the cost change if we nudge this one weight by a tiny amount while holding all others fixed? Collect all these partial derivatives into a vector and you have the gradient vector, written as nabla j. In PyTorch, this entire computation is automated. When you call j.backward, the framework traverses the computational graph that was built during the forward pass, applies the chain rule at every operation, and stores the gradient in each parameters.grad attribute. One call computes all gradients simultaneously. Here is a crucial insight that many beginners miss: minimizing the training cost is not the actual goal. The goal is minimizing the cost on new, unseen data. Overfitting happens when a model memorizes the training data so perfectly that its training cost approaches zero, but it fails completely on new examples. The model has learned the noise in the training set rather than the underlying pattern. Think of a student who memorizes the exact answers to last year's practice exam. Their score on that practice exam is perfect. But when they face the real exam with new questions, they fail because they never understood the underlying concepts. The fix is to monitor two costs simultaneously throughout training: the training cost, computed on the data the model learns from, and the validation cost, computed on a separate held-out set the model never trains on. As long as both are decreasing together, training is going well. The moment the training cost keeps falling but the validation cost starts rising, the model has crossed into overfitting territory. At that point, you should stop training. This is called early stopping. It is the simplest form of regularization and often the most effective. You do not need to modify the cost function formula at all, you simply stop gradient descent at the right time. Regularization is the technique of modifying the cost function itself to prevent overfitting. Instead of minimizing only the prediction error, you minimize the prediction error plus a penalty on the model weights. The total cost becomes J data plus lambda times R of W. J data is your original MSE or cross entropy. R of W is a regularization term that penalizes complex models. Lambda is a hyperparameter controlling how strongly you apply the penalty. L2 regularization, also called weight decay, sets R to the sum of all squared weights. Every weight is pushed toward zero at each gradient descent step. The effect is that no single weight grows very large, the model cannot rely too heavily on any one feature. Large networks trained with L2 stay controlled and generalize better. L1 regularization sets are to the sum of absolute values of weights. The gradient of the absolute value is the sign function, it pulls every weight toward exactly zero with a constant force. The result is sparsity, many weights actually become zero, effectively removing those connections. L1 performs automatic feature selection. ElasticNet combines both, alpha times L1 plus 1 minus alpha times L2. You get the sparsity of L1 with the stability of L2. Dropout is a different approach that achieves the same regularization effect without modifying the formula. During each forward pass, a random fraction of neuron activations are set to zero. The model can never rely on any particular neuron, so it learns distributed, robust representations. Now let us see exactly how the cost function connects to backpropagation in a neural network. During the forward pass, data flows left to right through the network. Input features enter, get multiplied by weights, pass through activation functions in each hidden layer, and finally produce the output predictions y-hat. This is the forward pass. Once we have the predictions, we compute the cost. J equals the loss function applied to y-hat and the true labels y. For regression this is MSE. For classification this is cross entropy. The cost J is a scalar, one number. Now backpropagation begins. We want to know, for each weight in the network, how much did it contribute to the cost? That is the partial derivative dj over dw for every weight matrix W. Backpropagation uses the chain rule of calculus. At the output layer, dj over dw output equals dj over dot times dot over dw output. These are both computable. Then we propagate backwards. At the second to last layer, we multiply by the local gradient at that layer. At the layer before that, we multiply again. Each multiplication applies the chain rule one more step. By the time we reach the first layer, every single weight in the network has a gradient stored. In PyTorch, this is the entire computation performed by J.backward. One call, and every gradient is computed in one efficient backwards traversal. Once you understand the building blocks, you can design cost functions for any task imaginable. The only hard rule is this: the cost must be differentiable everywhere your model might land during training. Multitask learning combines multiple objectives. A self-driving car model might simultaneously predict the steering angle, a regression problem, and classify the scene as highway or city, a classification problem. The total cost is a weighted sum, W1 times J steering plus W2 times J classification. The weights balance how much each task contributes. If one task has a much larger loss scale, it will dominate training and the other task will be neglected. Careful weight tuning is essential. Weighted cost functions address class imbalance. If your dataset has 99 normal examples and one rare anomaly, a standard MSE will ignore the anomaly. You can assign a higher weight to rare class samples in the sum. Focal loss, developed for object detection, takes this further. It automatically downweights easy examples and focuses the model on hard ones. In computer vision, perceptual loss functions measure difference not in raw pixel space but in feature space. You pass both the prediction and the target through a pre-trained VGG network and compute MSE between the extracted features. This produces sharper, more visually coherent outputs than pixel MSE. In speech and text recognition, connectionist temporal classification loss handles variable length sequence alignment. Segmentation tasks use dice loss or intersection over union loss to directly optimize the overlap between predicted and true masks. Let us compare all the major loss functions side by side to build a clear decision framework. For regression, predicting a continuous number like a price or temperature mean squared error is the default. It is convex, differentiable, and well-behaved. Use it unless your data has significant outliers. If outliers are present, switch to Huber loss as your first alternative. Pure MAE is available, but its constant gradient makes it harder to train deep networks. For classification, predicting a category, cross-entropy is the universal default. For multi-class problems with a softmax output, use categorical cross-entropy. For binary yes-no classification with a sigmoid output, use binary cross-entropy, which in PyTorch is BC with Logit's loss. For support vector machines and margin-based classifiers, hinge loss is appropriate. For generative models and probability distribution matching, KL divergence or variance of it are standard. Variational autoencoders use a combination of reconstruction loss plus KL divergence to the prior distribution. The most important mistake to avoid is using MSE for classification. When your output is a probability between 0 and 1, MSE has very small gradients near the extremes, the saturation problem. Cross-entropy loss does not suffer from this because its gradient is proportional to the prediction error directly. In PyTorch, these are all one-liners: torch.nn.mse loss, cross-entropy loss, BC with Logit's loss, and Huber loss with a delta parameter. Let us put everything together and look at a complete PyTorch training loop where the cost function plays its central role. The outer loop runs for a set number of epochs. Each epoch is one full pass over the training data set. Inside the epoch, we fetch a mini batch of samples from the data loader. First, the forward pass, we call the model with the batch input and get predictions y hat. Then we compute the cost, j equals criterion of y hat and y. The criterion is whatever loss function we chose: MSE loss, cross-entropy loss, or Huber. Notice the print statement: we log the current cost value to monitor training progress. Watching the cost decrease over epochs is how you confirm that training is working. Now the critical 3-line sequence. First, optimizer.0grad. This clears the gradients stored from the previous iteration. PyTorch accumulates gradients by default. If you skip this step, gradients from the previous batch are added to the current ones, causing incorrect updates. Second, j.backward. This is backpropagation. PyTorch traverses the entire computational graph from j backwards through every layer, applying the chain rule, computing dj over dw for every single learnable parameter. After this call, every param.grad is populated. Third, optimizer.step. This applies the gradient descent update, w equals w minus learning rate times gradient, for every parameter simultaneously. For Atom Optimizer, it also updates the momentum terms. These 8 lines train any neural network of any size. The architecture might have hundreds of layers. The dataset might have millions of samples. But the loop is always this. Let us review everything we covered in this video. The cost function j is a scalar that measures how wrong the model is. Lower is better. 0 is perfect. Without it, no learning is possible. MSE mean squared error is the regression standard average of squared prediction errors. It is convex, differentiable, and penalizes large mistakes heavily. Cross entropy is the classification standard, negative log of the predicted probability for the true class. It penalizes confident wrong predictions catastrophically, which is exactly what you want. MAE takes absolute errors instead of squared, more robust to outliers but harder to optimize. Huber loss combines both, smooth and quadratic for small errors, linear and robust for large ones. The loss landscape is the surface of J plotted against the weight values. Gradient descent rolls down this surface toward the minimum. The gradient of J, computed by backpropagation, tells every weight in the network which direction reduces the cost. J.backward does this in one efficient pass. Overfitting happens when training cost is near zero but validation cost is high. Always monitor both. Regularization modifies J to add a penalty, L2 shrinks all weights, L1 zeros many weights, dropout adds stochastic noise that achieves the same effect. The training loop is, forward pass, compute J, 0 gradients, backward pass, update step. Repeat for every batch, every epoch. That is the cost function. Not just a formula, it is the signal that teaches every parameter in the network what to do. The next video in the Maths Behind AI series goes deep into gradient descent, how the optimizer follows this signal to minimum. Subscribe to Neural Monk. See you there.